Good morning. Time for solids revolution, specifically the disk method. So normally I kind of explain what's going on and I jump into problems to show you, but we're just going to jump straight into problems. There are two common ways of doing solids and calculating the volume. One of them is generally referred to as the disk method. The other is referred to as the shell method. There are formulas that go along with each of them, but I don't even bother. I think they are self-explanatory enough that you're better off just jumping in and not winging it, but using experience to kind of just figure out what's going on. So we're going to start with the problem. Y equals 2 minus x. We're going to revolve it around the x-axis, and we're going to find the volume of the solid created. So get an axis like this, copy paste, move it to the side, and we got ourselves an x-axis. Give ourselves orange. Nope, not there. Let's do a y-axis. We'll do an x-axis. Probably should have arrows. There we go. Add a little bit of realism. So then we have 1, 2. Y equals 2 minus x. And that would be, since it's a line, that is a terrible line. About like that. Click. Make straight. There we go. And the idea then is we're going to have y equals 2 minus x. So we have negative x. Rise over 1 will be negative 1y for each positive x. So it'll be down. And then we're going to revolve it about the x-axis. So the solid will look something like that. Be down just a little bit further. There we go. Copy paste. Do one more circle. Nah. Oh. There we go. So what we have is a cone. It looks kind of like this. And the idea is we want to try and find the volume of this cone. Y equals 2 minus x. Yep. Boom. Okay. So what we're going to do is called the disk method. We take, for a random cross-section like this, it's going to be dx. And we're going to find the area of this cross-section and then multiply by a small amount, dx. Then we're going to integrate that small amount from 0 to 2. So we know what this height right here will be. This height right here will be 2 minus x. But that height will also be the radius of our disk. So if we want to find the area of the circle, the disk that we've created, it will be, is it pi r squared? I think it's pi r squared. Pi big R squared times dx. And this is the, so this part here will be the area of each circle. Then we multiply it by dx. What we do is we then make it a volume. And we're going to do that from 0, right here, all the way up to 2. Because when x equals 2, then y equals 0. And that's the intercept point. So we have this volume, minute small volume, because of the dx. And we're going to integrate from 0 to 2. And the idea here is this pi r squared, that's basically the formula they're going to have for the disk method. And all it is finding the area of the circle and then integrating. So this dx becomes, this delta x becomes dx. But I'm just going to ignore it. Ooh, wait a second, we need to get rid of that r. Okay, so we know that r equals 2 minus x, 0 to 2, pi 2 minus x dx. There we go. Yep. So we'll still have 0 to 2 pi, though I could bring it out. 4 minus 4x plus x squared dx. Okay, so what happened there was I wrote the formula in terms of r. You can use any variable you'd like. The idea was we just wanted to find some way of finding the surface area of the cross section, and then we took that r and then we related it to the graph, the data that we have that we were given. And then when we plug that in, did I forget a squared? That's supposed to be squared. Then we plug it in so that all we have are values of x. Then it's easy to integrate the dx with the x's, where r is a function of x, but we're really not entirely sure until we plug in our values. Okay, and going through this, so we'll have a pi here, we'll have a 4x, we'll have a 4x squared over 2, and then we'll have an x cubed over 3, evaluated from 0 to 2. Yep. So when we plug in 2, we get 8, that's 4 times 2, minus 4 times 4, that's 2 squared over 2, plus 8 over 3. Because 2 to the third is 8. And I'm going to leave off the zeros, because 0 times 4, no matter how many times you square 0, will still be 0. Man, now I'm thinking about that. I'm like, what if you square 0 10 times? No, still 0. Things that keep me up at night. Okay, so this is 16, but divided by 2, that becomes 8. 8 minus 8 is 0, so we have 8 thirds pi. And that is the volume of this shape right here, the cone that's kind of sideways. Y equals 2 minus x, revolved around the x-axis. Okay, pretty straightforward. And I don't know if you guys can see why I frown on trying to memorize formulas for this, because to me, I'm like, okay, we're going to break up into small sections, and what we're actually doing is we're building a pyramid that's more like, it's a cone, but like a cone that's like Egyptian style pyramid, where you're actually using blocks instead of smooth lines. But then when you get infinitely small blocks, then it becomes infinitely accurate. So it's like you're using delta x for an approximation, you get an infinitely good approximation, that approximation now becomes exact. And that's the concept that we're doing here. Okay, let's do a couple more. Thank you, y equals 2 minus x. Your days of utility are gone. Whoop. I feel so brutal doing that. Just disregarded, thrown to the wind. Okay. So now we have... I should have left my axis up there. Amateur. Okay. Actually, I'll draw this one. So we have... Come on, straight lines, don't fail me now. Surprisingly adequate. We have a y up here, x over here. And we have y equals x squared, kind of like that. And then y equals x, kind of like that. And they're going to intercept where x squared equals x, x factor out, equals x times 1, x equals 0, x equals 1. Okay. And then when we plug in 1 on the y side, we also get 1. It's not a terribly complicated graph, but yeah, it's good. I like that. I like it. Okay. So now we're going to revolve this about the x-axis. Now this is, so we want the area enclosed with the revolved around the x-axis. So we have this area here, and then we're going to do a circle like this. So similar to a cone that we did last time, except now it's facing the other direction, and we have an interior part that we need to take into account. This is sometimes called the washer method, where the idea is instead of using disks, you do washers, which is basically you take out the middle part. I don't usually like to use that phrasing. I call this the disk minus disk method, because that's all you're doing, is you're taking purple. I got so many colors, it's going to be hard to differentiate. So you're going to draw delta x. Your disk is going to look like this. This will be your delta x. And you'll take this value minus this value. So I'm going to start off with the same idea. We're going to have an integral, and it's going to go from 0 to 1. We're going to use a disk method. So I'm going to do pi r big squared minus pi r small squared dx. So then you can, let's see here. First I'll find what r big is. So the big radius, that right there. And hopefully this makes sense. So we have a big circle minus a small circle. And then we're multiplying both of them by a delta x. Or I wrote dx here. So the big circle will be y equals x. Since y equals x is bigger than y equals x squared for 0 to 1. So r big is x squared. R small, r big equals x. R small equals x squared. And why do I draw the x's different? Hope that doesn't mean I'm a psychopath. I don't know. I'm pretty sure if you're worried about being a psychopath, then you are by definition not a psychopath. Pretty sure psychos don't care that they are psychotic. Is that true? I don't know. I should investigate more. Further investigation is required. Alright, so we have pi factored out, x minus x squared equals... Yes. So then we'll have x squared over 2 minus x cubed over 3 from 0 to 1 times pi. And again, we'll have pi. And then I'm just going to ignore the 0 squared and 0 cubed, because those will both be 0. So we'll be left with 1/2 minus 1/3 times pi, which equals... What does this equal? Should I know this? Maybe I do know this. Okay. We'll convert everything to 6's. So pi 3 over 6 minus 2 over 6 equals pi over 6. Okay. Huzzah. I think that is correct. No, wait a sec. I forgot to square everything. Outrageous. Sorry. I just led you guys astray. Probably got distracted with my talking and such. Okay. Focus. So what we have here then is x squared and x squared squared. Pi 0 to 1, x squared minus x to the 4th dx. Alright, make sure I actually got this right. R x squared squared pi. Okay. So now we have pi x cubed over 3 minus x to the 5th over 5. Yep. There we go. And this is 0 to 1. So now we have pi 1/3 minus 1/5. And 1/3 is bigger than 1/5, so that's good. And now we're going to go to 15s for the denominator. So 1/3 of 15 is 5/15 minus 3/15. And we have pi times 2/15. There we go. Another parentheses over there. 2/15. Yes. There's probably some valuable lesson about here about things that are really easy to miss, that when you plug in. So, in case those of you who didn't notice what I did there, the bad thing that I did there that you probably shouldn't do. So when you plug in your x values, r big and r small, make sure that you actually follow what r says there. So in this case, it's r squared. Okay. Whoop. No, too much. There we go. Delete. Nope. Now I'm lost. There it is. Problem with the infinite boards is when you get lost, you can get really lost. Okay, and now here we have the same idea, except now we're going to use the y-axis instead of the x-axis for the revolution. So, here we go. Here's an axis. This one will be x. This one will be y. And we have, again, y equals x and y equals x squared. A little bit bigger. There we go. We still have the points of 1, 1, and 0. That looks terrible in there. Not very... And I'm going to move this y over. There we go. That one little dot seems to be bothering me. Okay. Put y up top. And the idea is we have the same curves, but now we're going to revolve this time around the y-axis instead of the x-axis. And intuitively, you think you should get a little bit more volume here because this is going to be bigger. Because before, we had the extra... so you think of the y equals x as kind of like the cone. Before, we had a little bit of the extra volume on the inside of the cone. We revolved around the x-axis. But this time, since we're revolving around the y-axis, it's going to be around the outside of this cone that we have, the y equals x. So this is x, and this is x squared. Yeah, I think that is probably a little bit sharper than it normally is in life. So, let's see, maybe over here. So we're going to go through the same process, except correctly. So we go from 0 to 1, because this time we're going to try and go along the y-axis, because it's, if you look at the way you'd have to make discs, the circles would have to go from 0 along the y-axis. So we're going to make our circles like this, and we'll be using dy's. And the top part is 1. And let's see here, what else? So we'll do r big right here minus r small. They're supposed to overlap, but if I overlapped them, it'd be more difficult to see. So I'm still going to use the disk minus disk method. R big squared minus pi r small squared, and then we'll do a dy. Delta y. I know I abuse notation. I apologize for nothing. So this time, the r big is y equals x squared. So we have y equals x squared. So r big equals x squared, but we want it in terms of y. So finding it in terms of y, square root of y, which is y to the 1/2, equals x. So r big equals y to the 1/2. And your thought process is, why can't we use x squared instead of y? Why do we need y instead of x? And that's because we're integrating in the y direction. Saying x or y to the 1/2 or r big, it's all saying the same thing, except to make the calculations work, they need to be consistent. So you could say that you can write x in terms of y, you can write y in terms of x, or you can write the r big, which is just a variable that we made up to kind of keep our mind straight. They're all the same. They can all do the same thing, except if you're going to integrate with respect to y, you need to have everything here to be y. And if everything there is not y, then we'd have to start doing things like, not the chain rule because that's derivatives, but substitution, it becomes very messy. So a mess we want to avoid. Okay. So rewriting this, and then also y equals x for r small. Change colors. So I have 0 to 1 pi. R big is y to the 1/2 squared minus y to the normal to the 1 squared dy. And integrating with y is very similar to integrating with x. It's all just a variable. This becomes 1. So we have y squared over 2 minus y third to the third over... Oh, this is where I'm going to get it at pi over 6. Okay, 0 to 1. I'm going to ignore the zeros again because for the zeros, 0 squared and 0 cubed is 0, despite being divided by 1/2 or 3. So we're going to have 1/2 minus 1/3. And that becomes pi 3 over 6 minus 2 over 6 pi over 6. Huzzah. Okay, now let's erase a little bit of this. I feel bad calling it clutter, but there is a lot of data on there that we don't need right now. Clickety clack. Okay, so one more problem. Woohoo! Aha! All right. So lock this in place. Ooh, this looks tough. I should grab a drink first. Crystal Light. Delicious. It's not real Crystal Light, of course. It's the cheap knockoff version. Great value. Probably. Let R be the region in the first quadrant bounded above by the graph of y equals natural log of 3 minus x. Okay? Or 0 less than x less than 2. Okay, so that makes sense because it'll basically start from natural log of 3, which is probably a little bit bigger than 1. And we'll move down to natural log of 3 minus 2, which is natural log of 1, which will be 0. Okay. R is the base of a solid for which the cross-section perpendicular to the x-axis is a square. What is the volume of the solid? Okay. So start by drawing a picture. Pictures are really nice in life. So we only have to worry about 0 to 2. 1, 2. And then we'll just do 1 to 2 on this side for the y-axis. We have natural log, y equals natural log of 3 minus x. Natural log of 3 minus 0 equals natural log of 3. And so natural log is going backwards from e. So e is like 2.7. So like I don't know, 1.2 is about 3. I should probably check that out. All right, natural log of 3 on Wolfram. And here we go. Natural log of 3. 1.09. Okay, so we're good there. Actually, why don't I just do the whole y equals natural log of 3 minus x. This will save me some time. Kind of goes down. Got it. So goes something like that. Okay, I'm good with that. And then it's saying that the The base of a solid for which each cross-section perpendicular to the x-axis is a square. So we're in the first quadrant, and I think what it's saying is, so this isn't a revolved solid. So it's saying that for each section here, we have a square, like this. So it's kind of a funny shape, where this is dx, and then this length here is natural log of 3 minus x, and then the top is also natural log of 3 minus x. And yep, so we're going to integrate along the x-axis, so integrate from 0 to 2, and we're going to have natural log of 3 minus x, and it's a square, so to find the area that will square it, and then we'll multiply by delta x. So see what I did there? So the idea here is we're going to take a whole bunch of cross sections. We know the height of the cross section because it's just the graph natural log of 3 minus x. We know it's a square, so that the width of these are going to be the same as the height. So we know that they're both going to be natural log of 3 minus x times natural log of 3 minus x. And then we know the width of each square is going to be delta x. And that's because we're going along the delta x direction. Because the cross sections are perpendicular to the x-axis, and it's easiest to go, much easier for us to go in the x direction than trying to go in the y direction. And your first thought might be, well, this isn't a solid or revolution at all. That's true, it's not. And I think this is a good example of why I don't memorize the formulas for the disk method or the shell method or the disk minus disk method, the washer method. Because it's easier just to visualize the shapes and be like, all right, I have this 2D shape visualized, and then you add some dimension to it, add some depth to it by throwing in a delta x or delta y or delta whichever direction you'd like. Okay, so we can solve this. I'm pretty sure, so if you remember, the integral of natural log of x was x ln of x minus x. And I'm pretty sure, and we used integration by parts, I'm pretty sure you can do something similar with this, but you'd have to do a substitution and then do some integration by parts, and it could be a while. But on this section, you'd be allowed to use your calculator. And part of the giveaway is you have 3 decimal places here. So let's just pull out the calculator and see if we can do this. So, using our trusty calculator, huzzah! Oop, there we go. TI 83 plus. I hate these calculators. I know. They are a marvel of science. Okay, so we could just plug in. I'll do a parentheses, maybe a natural log, 3, a negative, an alpha, an x. Another parentheses, and a square. And then, let's see, the window we're going to want will be 0 to, I'm going to say 8. Just because I don't want it to be too close, because then when I start tracing the graph, I'd have to go all the way across the window. But we know we're only going to have to go from 0 to 2. And then we know that the y value is only going to be like 0 to 1 something. So delete u, 2, and then we'll graph. It goes whoosh. This is the only part we're concerned about right there. That, yeesh. Okay, so then we'll do second calculate. We'll want the integral portion. Integrate. Find the lower limit. Alright, so it's over by 3, so we're going to have to work all the way over. There we go. Come on, you're so slow. Quit being so slow. There we go. Lower limit. Click, click, upper limit. Now one of the things we might want to be careful about here is we don't want x to go past 2, because at ln of anything higher than natural log of, just higher than natural log of 2, we get natural log of a negative number. And we don't want to cross that threshold. I don't think this calculator is that smart. So 1.95 is good enough. Can I get closer? Yep, 1.95 is good enough. Okay. Zing, zing, zing. The little Riemann sums. And we get 1.029. Which I think is one of our 029. Whoop. Yes. And it is. So, go back to our calculator. 1.029. Yep. And so what we did there was we set up the integral using squares instead of circles. And then we just calculated it through the brute force of the calculator. And so the trick here is being able to set up the integral, not actually, and then being smart enough not to solve it. Because though you could solve that, man, that would take you a long time. You don't have time. This is like a 2-minute problem, so you need to move quite quickly. And the hard part then would just be knowing that this is the way you want to make your squares. Okay, and that's enough for the disk method. Next time we'll look at the shell method. Thanks.